Spectrum of natural frequencies and main modes of free vibrations of frame with two concentrated mass. It's article number 11.5 of the book Mechanical Systems Calculations of the Marine Facilities. Let's consider the mechanical system of two concentrated masses M1 and M2 on the elastic, statically definable frame supported in two hinges. The left one hinge and the right one. The width of this frame is 2 meters. The height of the location of the second load 2 meters. The horizontal beam on the hitch 3 meters, and the console 1 meter, and the attachment of the next mass, first mass, on the console. So this masses can, by the bending of this mechanical system, can move in the directions y1 and y2, and assign that the mass of the first mass equal to m and the second mass equal to 2m, and the stiffness characteristics of the vertical stance are modulus of the elasticity by the moment of the inertia of transverse section, and of the horizontal beam equal to the product of 2 by modulus elasticity and the transverse section moment of the inertia. And mechanical system, the frame has 2 degrees of freedom. The displacements of loads y1 and y2 during elastic deformation of the frame. So on it has no the degrees of freedom on the geometric aspect as a rigid body, but as an elastic body, it can move while bending in the directions y1 of location of the first force and direction y2 of location of the second force. And it is assigned to find the frequencies of natural frequencies of the oscillation of this mechanical system, the eigenvalues of the characteristic equation, etc. To have the decision, first of all, we have to consider the characteristic equations of free vibrations of loads. The characteristic equations are the first equation, the second one. In the brackets, we have the product of the mass on the displacement in the direction of the possible displacement of the first mass and the actionable unit load in this direction applied. Minus the eigenvalue is a subject of determination using the characteristic equation, so we just indicate eigenvalue, and after the brackets we multiply by the amplitude of the oscillation of this mass as well, subject to determination, and plus the product of mass multiplied by the unit displacement in the first direction and the action of unit force applied in the second direction, and multiplied by the amplitude of the oscillation in the second direction. And the second equation, characteristic equation, these characteristic equations got by the force method of the deformation, considering the forces of the inertia applied to the oscillating masses. We neglect the mass of the frame itself. We just only consider the stiffness of the mass of the mechanical system and consider the masses of the concentrated loads. So having the force method equations, equality of all forces action on each direction, considering as well the forces of inertia, as look like the Lambert concept of the balance of the bodies moving with acceleration, we can, after the mathematical transform, have this system of the characteristic equations. And the second equation is the multiplication product of the first mass by the displacement in the second direction, the action of the unit displacement and the action of the force applied on the right in the direction of the oscillation of the first force. Plus, in the brackets, we have two summand. We have actually difference. The first summand is the mass of the second force multiplied by the unit displacement mass, not the second force, but the second mass, multiplied by unit displacement in the direction of oscillation of the second mass, and action of the assumed unit force applied to the same direction to the point of location of second mass, minus the eigenvalue as a result of decision of the characteristic equation, and multiplied by A2. A2 is the amplitude of the oscillations of the second mass. These characteristic equations as well have the matrix form, matrix type of the formula. The matrix type is in the brackets. We have the matrix of the amplitudes A1, A2, A1, A2, and this matrix minus the characteristic result of the decision of characteristic equation, the eigenvalue of the characteristic of the oscillation lambda, multiplied by the diagonal unit matrix of diagonal of units are the zeros, and this in the brackets, and out of the brackets we multiply the brackets on the eigenvector of the oscillations. Eigenvector consists of two amplitudes. In the different one case, it can be many amplitudes for any case. They have to be equal to zero. This is could be the matrix type of the characteristic equation, not only the type of the characteristic equation as the system of the equations. To use these characteristic equations to find the eigenvalues of the oscillation, and in the next, due to we remember that the eigenvalue equal to the fraction 1 divided to squared cyclic frequency of free oscillation. So we need to have this eigenvalues to find the spectrum of frequencies of free oscillation of the considered system. So to use these equations, we have to find first the displacement and action of unit forces. This delta lowercase 1, 2 equal to delta lowercase 2, 1 due to the property of the reciprocity of this displacement in the first direction and the action of force in the second direction, and then second direction and the action of force applied in the first direction. So next, let's find these three factors: delta 1, 1, delta 2, 2, and delta 1, 2 equal to delta 2, 1. So let's consider the assigned system and the action. This is a statically definable system and the action of unit forces. The first force applied in the direction of the oscillations of the first mass, and second force applied to the point of location of second mass in the direction of the displacement of oscillations of the second mass. This statically definable system, so we can consider the balance equations. For example, relative this one point, the left one hinge, and action of the first force, we assuming that the arm of the first force, unit force by the arm is 1 at the console, and 3 is a vertical stand. Together the arm is 4, 1 plus 3, and this horizontal size of the mechanical system is called 2. So force unit force causes the reaction at the second hinge as 2 due to the arm is twice less. After that, we can find the projections of all forces on the vertical axis, for example, and we can find that the support direction in the first hinge is 2, but directed to another direction due to the support reactions have the projections on the vertical axis and the action of this unit force. And we'll consider the projection of all forces on the horizontal axis, and we can find that the component of the horizontal the horizontal component of support reaction in the first hinge is 1 due to the another force is 1, 2. For the second point of the application of unit force, we can consider the balance equations relative. For example, this one point, the rotating moment have to be equal to 0, so the force rotating clockwise 1, the support reaction to the same arm, 2 meters here, 2 meters here. the subportation is one, but directed to another direction, rotating counterclockwise. So next, consider direction of the second unit force. The projection of all forces on the vertical direction, we can find that the second support direction is 1 as well, directed opposite to the first one support direction. And next, let's consider the projections of all forces onto horizontal axis. We have force rightward unit force, and we have the leftward support direction on the no other forces we have under action we have with the horizontal components under action of the unit force in the second point. So to find the displacement of the unit force, we have to use the Moore integral. Moore integral is total by the elements of the mechanical system of integrals. For each of the element mechanical system, we have to find the integral. In the numerator, we have the product of the diagrams. In the denominator, we have the characteristic of elasticity of the transverse section of the each element considered. So the product of diagram we can find perhaps by use of the any rule usual, like could be Vereshchagin rule to find these products of the diagrams. Exactly, we can have the direct finding of the Moore integral, but to do that we have to introduce in the this mathematical equation the direct determination of the diagram, but we usually have only the ordinates of the diagram. This linear diagrams of the bending moment. This bending moment diagrams are the action of unit force, one and the second one unit force. If we have to find, for example, the displacement in the first direction and the action of unit force applied in the same one direction, we have to use only these diagrams, and we multiply these diagrams within the Moore integral by themselves. So let's consider the determination of displacement in the first direction and the action of unit force applied in the same one direction. So first is a factor of the characteristic of the elasticity. In the denominator, we have the elasticity modulus and the moment of the inertial transverse section of the transverse section of the element mechanical system. For definite one case, we consider the vertical stand. Each has h 3 meter and the diagram equal to 3 y3. The force of 1 caused by the arm of 3, the moment equal to 3, and this diagram is linear. This force of 2 by the arm of 2 cause the diagram 4. It do not cause the diagram on this one vertical stand due to the line of action of the force coincides with the definite one stand axis. And this is exactly 1 due to the arm is 1 and the force is 1. So it's very easy to explain how to find these diagrams of the bending moments. So for this one stand, 3 by 3 divided by 2, this area of this triangular, 2/3 by 3 is the magnitude of the diagram in the point of the maximal, or in the point of the center of the area of this diagram. This is Vereshchagin rule use. And plus for this small one diagram, 1 to multiplied 1 by 1 is the area of the diagram, and 2/3 by 1 is the ordinate of the diagram bending moment here in the point corresponding to the center of the area of the diagram. And for this one triangular diagram, the elasticity is twice bigger of the horizontal beam. This assigned 1/2 multiplied by 2 by 4, this area of this triangle diagram, multiplied by 2/3 by 4 is this 4 is the maximal magnitude, and this is 2/3 multiplied by 4 is the diagram ordinata in the point of the area is the center of the area of the diagram. Finally, we have that the displacement 1, 1, unit displacement delta lowercase 1 1 is equal to 44 divided by 3 by E modulus of elasticity and divided by I is the moment of the initial or transverse section. So let's, for example, find delta 1, 2 or delta 2, 1. This equal as the reciprocal equal to. We have to multiply this diagram by this one diagram according to the Moore integral. The first summand is the product of this for this one part of the stand 3 by 3 by 1/2 is the area of this one diagram, and for the center of this area the magnitude is 3 multiplied by 3 2/3 of 3, yes, plus for the horizontal one segment we consider the area of this diagram 2 by 4 and divided by 2. This is area of this 2 by 4, 1, 2 part. And multiplied in the brackets, this finding of the magnitude of this trapezoid, considering the point of the location of the center of the area of this one triangular shape diagram. This is a formula to finding of the magnitude of the trapezoid for definite one place, 1/4 part from the left and 2/3 from the right. That's why 1/3 part from the left and 2/3 part from the right is the central location of area of this one triangular diagram. So we do not consider finding delta 1, 2 and delta 2, 1. This triangular diagram due to the second one is 0 and the product of diagram had to be 0. And this one triangular diagram, and on this piece of the vertical stand, this 0 diagram, so product equal 0. So the final result delta 1, 2 and delta 2, 1 equal to 23 divided by 3 by E by I. And delta 2, 2. So the displacement in the second direction, in the location of the second mass, and action of unit force assumed applied to the second direction to this point of the location of mass. Yeah, first is the product by use of the Vereshchagin rule of this one diagram by itself as 3 by 3 divided by 2. This is the area of this triangular diagram, and the ordinate is 2/3 product by 3 plus, excuse me, product by 3, yeah, plus for the horizontal we have trapezoid. We divide trapezoid into triangular shape, two pieces of triangular shape, and for each we do use a Vereshchagin rule, but this just only the ordinate located 2/3 part from one side and 2/3 from another one side. So the ordinate of this this component of this trapezoid, and this triangle trapezoid component as well consists of ordinate located 1/4 part to right 1 point and 3/4 from left 1 point. So in the brackets we have the use of the Vereshchagin rule to find the product of the diagram trapezoid by itself. And plus for this small one piece is just the area of this small one piece, and 2/3 part magnitude of this diagram corresponding the point of the location of that area. So we can find the last one, displacement delta 2, 2, and in the second direction, and the action of unit force applied to second direction. Okay, and we little bit transform the original equations. Let's transform this. Instead of the eigenvalue, let's consider the generalized parameter, which equals to the eigenvalue multiplied by the characteristic of stiffness divided by mass. So like this one, consider this parameter. This just to simplify the type of the equations we have. So finally, after the substitute of the unit displacement and after doing this mathematical transform, we have raised a simple system of the system of the characteristic equations like his simplified. We substitute found displacement in the definite one directions one direction, the unit force in the second one direction, and we substitute the eigenvalue by the generalized parameter. So let's find the generalized parameter as the right side of the equation is equal to 0. We have the rule. We have to find the determinant of the matrix of factors to A. A is the matrix of the amplitudes, and the factors to the amplitudes we consider as the elements of matrix of the factors, and the determinant of this matrix is equal to 0. When discover this determinant, we multiply these brackets to this bracket one minus this 23 multiplied by 46, and finally we found that the characteristic equation is indicated here. And deciding this equation, we can find that the generalized parameter equal to 9625, or 20, and this we have to, due to the using the decision of the algebraic square degree equation, and using the determination by the determinant of this, finding this is known rule how to find the decision of the quadratic equation like this one. And we have first decision 96.25, and the second decision of the generalized parameter 2375. And when we substitute this generalized parameter into the transform, finding this by the eigenvalues of the characteristic equation, and considering that this eigenvalue of the is equal to 1 divided by the natural cyclic frequency squared in the denominator. So after all this transform, we can find the cyclic frequencies of the free oscillations of the two-mass elastic system as this the two decisions of this equation. So this is a use of the property of orthogonality of the main vibration modes. This is a spectrum of the oscillations. We consider the property of the orthogonality, those like this superposition of other vibrations, and characterizes by the one of the corollary, one of the corollaries due to decision of the characteristic equation. That is the oscillations are orthogonal. That is the total for each of the masses of the product of the mass by the amplitude of the displacement of the mass in the oscillations of the one mass, and the product by the amplitude of oscillation the same mass, and the influence of oscillation of the another mass have to be equal to 0. This I not equal to k. So considering that, we for the characteristics of the mechanical system can find two amplitudes. First amplitude equal to 23 by 1, etc. And this is a linear equation. You can find that the amplitude of vibration of second concentrated mass, and the action of the oscillation of the first mass, and the amplitude of the oscillation of the second mass, and the action of itself. It have to be of the another signs. And for assigned to mass mechanical system, the eigenvectors, vector of the amplitudes of two main modes of the vibration equal to this is one eigenvector, and the second eigenvector 1 and 1.3058. The amplitude of the vibration of one mode, and the second mode is 1 and minus 0.4402. So we can look if we have the amplitude of the vibration of first one mass. This have to be assigned as the amplitude of the vibration of the first one mass because the exactly the amplitude depends on the initial condition. So we have to apply the initial conditions. If not, we cannot find this elastic system. The amplitude depends, amplitude and phase, initial phase depends on the assignment of the initial conditions. So we can verify the main vibration modes for the mechanical system considering the oscillation of the another point. So it is equal to 0. The works of the oscillation of other mode, of one mode, do not impact on the work of the forces in the oscillation of the another mode. So we can consider the oscillation as independent. And as well, we can use the very common to use the Mathcad computer algebra system. For decision characteristic equation, this is very convenient to do, very comfortable. We to find the eigenvalues of, we have to find the eigenvalues here, like lambda here, and this corresponds to to finding of the amplitude of the oscillations. We first have to find, actually we have to specify the matrix in the Mathcad of the elasticity. Matrix of elasticity is delta, and the matrix of the masses 1 and 2. This assigned. This we got due to consider the statically definable system and consider the displacement and action within forces. And will it with this transform due to we deduct the factor of the modulus of the elasticity. Just consider only the decisions with not the modulus of elasticity and with not the considering the stiffness. We consider the stiffness, but we do cancel this due to these common factors for all of the equations. This is vector and actually the matrix of the mass to do the product to this elasticity for the characteristic equation. We use the option in the Mathcad diagram. This is first we define what is the M. This is like a vector, and a diagonal M we have the matrix type of this masses vector M. Next, we define what is the amplitude. Amplitude is a product of the unit displacement by M. Next, having this, we can indicate in the sheet of the Mathcad what is A, the amplitudes are equal. Next, we have the unit matrix diagonal, and this assumes that we predetermined what is the system of the characteristic equations. In the Mathcad, we have in the brackets here assigned that is the matrix of the amplitudes, and the second is a diagonal matrix, and lambda here is a finding of the characteristics values if we assume that the matrix of amplitude is A and the matrix diagonal matrix is E. So in this case, the eigen values of the characteristic equation. So this is just the operation with the characteristic equation is included in the concept of this operation in Mathcad, finding of the eigenvalues of the characteristic equation defined by these two matrices. And this easy that we can indicate the found result. It's very comfortable, easy to do, and very fast. Not so much of the efforts we have to pay. And we have the eigenvalues here, just the ready result after of doing this operation. And after that, we can find the agent vector. Agent vector is a vector of the amplitude of the same characteristic equation. After finding of the Gen values, we can find the agent vector of amplitudes of the vibration. This vector we have as a matrix, and this is amplitudes of the vibration. And so by this way, amplitude of the oscillation we have 1.3136, and this is equal to we got before 1.1358. I have 2136 is just a little bit degree of the approximation, minus 0.44, and here we have minus 0.44. So this is how to use the Mathcad computer algebra system to decide. Please look how this is easy. But the difficult part of the work is the definition of the flexibility matrix. We have to find first the flexibility matrix, because this have to be specified. Almost all other, and besides we specify the mass matrix, although the masses are specified originally, for the assignment. This we have to do ready to specify in the Mathcad. And all after is just a very formal and just the assuming that we working with the characteristic equation and finding for agent values or agent vectors. So the amplitudes of the oscillation. The questions and comments. 11.5.1 form of characteristic equation of free vibrations of an elastic frame with concentrated loads. It depends on how many concentrated loads we have, but the form is like equality to zero of the displacements. Considering the superposition of all displacements for each equation of displacement of definite one point of location of concentrated force, and the summons in the equation is the displacement and the actions of the force applied in the definite one point. The force, I mean the force of inertia, second derivative of the displacement. Force of the inertia, and the summons are the inertias, the forces of each concentrated loads. We are talking about the multi-mass system. This is forces of inertia of displacement of all forces, impact on each one, displacement of each other, displacement of the concentrated load. So the system of equations is of the number of the equations in the system equal to number of the concentrated loads. 11.5.2 determine of diagrams of bending moments and the action of the unit forces acting on elastic frame in the directions of possible motions of concentrated loads, and the use of more integral to find these motions, the elements of compliance matrix of system of the force method canonical equations. The unit forces, the displacement and the action of the unit forces, and the characteristic equations in the system of characteristic equations, the elements of the displacement and the action of unit forces form the flexibility matrix, flexibility or the compliance matrix. And to find the components, the elements of the matrix of the flexibility or compliance matrix, we have to consider separately the action of the unit forces in each of the points of the application of the concentrated masses, and to find the impact of this force on the displacement of all other masses, and this one and all other masses. To find the displacement and action of unit force, we can use more integral. This known approach as a product of the diagrams by the elements of mechanical system. We have total of the integrals of the products of the diagrams along the each element axis between the points of the connection with other elements. And the approaches to find more integral could be others, so it can be direct determination more integral if we have mathematical dependencies of the dependent moments on the coordinata to associated with each of the element of mechanical system. Or we can use, in the definite assumptions, we can use the method of Vereshchagin. If one of diagrams in the product of the more integral is linear, we can use the Simpson rule, if which is the correct and exact mathematical decision for the bending moment diagram up to paraboloid of second degree, parabolic shape of the bending moment diagram. We can use the trapezoid rule for the linear diagram multiplication in the integral of more. All the approaches to find, besides of the direct finding of the more diagram, is all other approaches, Simpson rule, trapezoid rule, Vereshchagin rule, is for use to find the product of diagrams if we have only the magnitudes of diagrams. If we do not have the mathematical equation, if we have mathematical equation, we can find the more integral directly. If we have no mathematical equation, we have to use any approaches like at least I told the Vereshchagin rule, Simpson rule, trapezoid rule. 11.5.3 a system of characteristic equations for determining of eigenvalues of free vibrations of an elastic frame with two considered loads. Grouping the eigenvalues with indicators of masses of the loads and the rigidities of elastic frame in accordance with the elements of the compliance matrix. The system of characteristic equations have the analytical form and the matrix form. The analytical form is that the total of the displacement after the transforms have to be equal to 0. The total of the displacements and the action of the forces of inertia on each of the considered masses of the multi-mass system to the displacement, the influence of the oscillation of all masses, and to the on the influence of on the the influence of the forces of the inertia of the oscillation of all masses on the displacement of each one mass. This is the characteristic equations, and we can transform this to the polynomial because these equations on the right equal to 0. That is the decisions finding the eigenvalues of the amplitudes of the oscillation. We can do only for non-zero magnitudes of the amplitudes. We can find only if the matrix of the characteristic value system factors to the amplitudes, this matrix of these factors determinant, algebraic determinant, have to be equal to 0. The discovery of the determinant leads to finding of the characteristic equation, and decision of the characteristic equation is the eigenvalues, and having eigenvalues we can find the natural frequencies of the oscillation of each of the mode of the oscillation of the multi-mass system. Sometimes we can simplify the type of the characteristic equation due to combining the complex of all the constants used in the factors of the characteristic equations, and we can find instead of the eigenvalues the generalized parameter, combining this eigenvalue each with the definite characteristic of the rigidity and mass of the mechanical system. Exactly when we find the eigenvalues and the eigenvector of the amplitudes of the oscillations, first we have to do the opposite transform and consider the rigidities and masses to find of the generalized parameter, to find the eigenvalues of the oscillation of the using the generalized parameter got by decision of the characteristic equation. 11.5.4 finds the determinant of the characteristic equation system given the roots of the final characteristic equation and determines the natural frequencies of Fourier oscillations to masses elastic frame. Finding of the determinant is easier for if we have two or three characteristic equations in the system, we can do this formal. If we have more, we have to use the approaches, maybe the options of the Mathcad computer algebra system, very comfortable, convenient to use, or maybe even the Microsoft Excel, but I can recommend Mathcad. 11.5.5, finding the amplitudes of natural vibrations to determine the spectrum, the distribution amplitudes or frequencies using the property of orthogonality, the main modes of vibration, the equality to zero of work of forces of one main mode of vibration on the displacement of other main mode. Yes, this is one of the corollary of decision of the characteristic equation that this correspond to physical concept that vibrations of all modes. So we corresponding each of the decision of the characteristic equation. I mean, each of the natural velocity of the vibration. The oscillation in the each of mode do not impact in the work of the forces in the other oscillation. So we can consider the work of forces in oscillations of other modes as independent. This we can use to find the amplitudes of natural vibrations. Having before got the decision of the characteristic equation and the eigenvalues and the natural frequencies, we can find the eigenvector. Eigenvector is a vector of the amplitudes of the oscillation. 11.5.6, using determination of the Mathcad using the eigenvalues operation of the vector of eigenvalues of square matrix amplitude serving the numerical coefficients, the eigenvalues amplitude matrix, by which the eigenvector of amplitudes when multiplied by amplitude matrix turns into itself in the properties of these coefficients. Exactly, the Mathcad computer algebra system have the ready options like a general option, or maybe not only general option, it has also the genvex option. Yes, and we just only if we have the matrices of the amplitudes having here like a product of displacement by the matrix of the mass displacement, unit displacement of the flexibility matrix by the mass, we can, this is considering together of the elasticity and the mass of the system required to find the characteristics of each oscillations as the characteristics of the natural frequencies, natural cyclic frequencies, like a spectrum characteristic of the oscillations. And this is already in the Mathcad computer algebra system. We can use this with not the lot of the efforts. It reduces and helps us to decide the system of the use of Mathcad helps us to decide the characteristics equations to find the eigenvalues, eigenvectors, amplitudes, and natural frequencies spectrum. Thank you.